It says wildlife conservationists are concerned that the deer population might not be constant across the national forest. The scientists found that there were 144 deer in a 16 square mile area of the forest. In another part of the forest, conservationists counted 117 deer in a 13 square mile area. Yet a third conservationist counted 216 deer in a 24 square mile plot of the forest. Do the conservationists need to be worried? So first of all, just thinking about this, talk in your groups for just a minute. Let's just think, why would this even be an issue? Why does it matter if a deer population is not constant in a certain area of the national forest? So go ahead in your groups and just think about that for a minute. When we talk about real world, why would scientists or conservationists be concerned that populations are dropping off in certain areas? Go ahead and talk about that for a minute. Okay, so let's talk about that for a minute. Why do you think conservationists might be concerned if the deer population is not constant across the national forest? Samantha, what do you think? Okay, so it could be that we have overhunting or maybe even just hunting if it's a forest preserve that you're not supposed to be hunting on. So perhaps overhunting or hunting could be causing problems. Anybody else come up with another reason why they might be concerned? Again, what do you think? Okay, so an overpopulation could hurt plant life. Got too many deer. Might end up having not enough food for them because they're going to kill the plants. Riley, what do you think? The deer could go extinct, right? If we have a dramatic drop, there could be that perhaps there's a problem that it started in a certain area and it's going to spread, and so we have to find out why is there a lower deer population in that area.
I have a question. What is plant deer?
Oh, I don't know. Plant deer? I meant plant life, but I said plant deer. There we go. All right. So again, this is something that scientists would be concerned about. That if they thought, hey, in one area of this natural forest, we have less deer than we should, we have more deer than we should, this would be something they'd want to know about. So it says, what is the population, the density population of deer per square mile? So for each of these different areas here with your group, we want to find out, for example, on the first one, there were 144 deer in 16 square miles. And so we could write that miles squared like that. Remember, anytime we would write a rate, we want to make sure that we put that in terms of, with labels, as a fraction with labels. We don't want to just leave it 14 over 16 or 144 over 16. Then what would I do to find out for 1 square mile how many deer there are? What would I do, Chloe? Divide it by 16. So go ahead with your group and find out for the other couple surveys that they did there, how many deer are there per square mile. Our unit rate every single time, that the scientists really didn't have anything to worry about because it was 9 deer for every 1 square mile each time. So it says the unit rate of deer per 1 square mile is 9. So when it says explain the meaning of the unit rate of this problem, what would that mean? What would that mean that when we say that? John, what do you think?
It's like kind of explaining what the fraction means.
Okay.
Top and bottom. So like the top was deer and the bottom was square miles, so it'd be
Okay, so 9 deer every 1 square mile. Now, does that mean that there's exactly 1 deer in each square mile out there in the forest?
No.
What does it mean then when we say that there's 1 deer per square mile? It's about that much, or on average it's that if we took all the deer that were out there and we gave them each their own square mile, we would, or they're, divided them into square miles out there, there would be about 9 deer per square mile. But again, it doesn't mean that there's exactly 9 deer every square mile. It's just kind of an on average. If we took all the deer and we added them up and then we split them among all the miles, that's where we'd end up. So it says use the unit rate of deer per square mile, and then this is the first time we're kind of seeing this idea, the y over x, and we're going to talk a little bit about that in a minute, to determine how many deer there would be every 207 square miles. So if we knew it was 9 deer in 1 square mile, what would we do to figure out 207 square miles, how many deer we're going to have there? Times 207. It was 1 mile. We want to change this 1 into 207, so we're going to multiply by 207. If I multiply the denominator by 207, I have to multiply the numerator by 207. And so 9 times 207 gives me about 1,863 deer in the 207 square miles of that whole area that we're looking at there. Okay. So let's say that we're talking about something a little bit different here. Let's say now we wanted to know how many square miles are we going to have to search before we find 486 deer. So if we use our unit rate of 9 deer per 1 square mile in your groups, go ahead and work on that. What would we have to do if we wanted to find 486 deer? What we would have had to do here is take a look at what 9 times what is 486. So how did you figure out what to multiply there to get from 9 to 486? Xander, what'd you do?
Okay, so I had thought that maybe if I were to divide the 486 by 9.
Yep.
To see if I could get what it would be, then I got 54, so then I multiplied it by 54 and got 40.
Okay, good. Exactly. That we know that operations undo each other, so if we're trying to figure out 9 times what equals 486, we should be able to divide by 9 to figure out that. Think back to our equations. What Xander basically said is he said 9x equals 486, so how do I figure out what the x is? I divide both sides by 9. You don't need to show that, but that's basically what we did there, something that we've been working on for a long time is equations. And so then 1 times 54, of course, is 54 square miles per deer. So again, we've done a little bit of this before. We haven't called it constant of proportionality, but the unit rate is the same as what we call constant of proportionality. So flip this over because there's a couple things that we want to talk about on here up there under that heading there. We already have talked about variables before, and we know that a proportional relationship, that whenever we have a proportional relationship, we have an ordered pair. We have an x and a y. And we haven't necessarily been calling it an x and a y, but we have been looking at tables where we've got 2 different things we're comparing. Days of the week and how much you read, or pencils and how much they cost. That we've got these 2 things that we're always looking at in our table. And so we could, instead of just labeling them what they are, we can call them x and y. And tomorrow we're going to talk in a little bit more detail about the equation that goes with this, y equals kx. Now if you look at this, y equals kx, again, this is something that we did on these charts. You didn't necessarily know you were doing that yet, but you were. This one here has y equals 40x. That looks just like what they have there, only instead of a k, they have 40. They have y equals 30.25 times x. Instead of the k, they've got 30.25. They kind of underneath there, y equals 26x. So this equation you guys used when we did the candy activity. But the k is what we've never done or talked about before necessarily. But right here it says the k is called the constant of proportionality. In your notes, I want you to do this. Outline it, highlight it, do something so you can mark it. And you need to know that when we talk about the k, when we talk about the constant of proportionality, what we're really talking about is the rate, which we've already done. So in your notes, mark that in some way. K is called the constant of proportionality. And when we're talking about constant of proportionality, we're really only talking about the rate, which we've already been talking about last week. And again, we know the x and the y can vary. That the x and the y could change. We found that out when we did the candy activity, that we could keep adding different how many pieces of candy we were going to have, and that changed how big that strip of wrappers needed to be. When we had, it also showed that sometimes you can take out that k, x, and y, and you can have, for example, you guys have probably worked with the distance formula before. Distance equals rate times time. Notice how similar that looks to y equals kx. Look at how the distance formula ties right in with y equals kx. So doing the example here, Braden came home from school and informed his mother that he had volunteered to make cookies for his entire grade level. He needed 3 cookies for each of the 96 students in 7th grade. Unfortunately, he needed the cookies the very next day. Braden and his mother determined that they could fit 36 cookies on 2 cookie sheets. So, is the number of cookies proportional to the number of cookie sheets used in baking? Create a table that shows the data for the number of sheets needed to the total number of cookies baked. So let's start with a table here. And we're going to have sheets and cookies. And I'm going to do a few examples on this here. So it says that they determined that they could get 36 cookies onto 2 cookie sheets. So for 2 cookie sheets, they can get 36 cookies. So how would I continue that table? What else would I know then? Samantha? For 4 sheets, how many cookies could they get on 4 sheets? 72. Trey, can you tell me how you got 72? Where did that come from?
It was 36 times 2.
36 times 2. So we did 2 times 2 is 4. 36 times 2 is 72. What about if they did 6 sheet of cookies? How many, or 6 sheets, how many cookies are they going to be able to get on 6 sheets? Wow, talk about that in your groups for just a minute, because I'm hearing all kinds of different answers here. Okay, let's look at this. Think about what we just were doing there, that if we had cookies proportional to sheets, we know, so 36 cookies on 2 sheets. Okay, that was my rate that they gave me. And again, when I look right here, is the number of cookies proportional to the number of cookie sheets? I know that the number of cookies has to be in the numerator and the sheets has to be in the denominator, because that was the order they gave it to me in. So thinking about what we just did, if I want 6 sheets of cookies, what am I going to have to do to get between 2 and 6? Times 3. So 36 times 3 is 108. So I would need 108 cookies per. So if you haven't already, go ahead and figure out, if we did 8 sheets of cookies, how many? Alright, so we should have gotten 144 here. So what would our unit rate be then? We know our rate that we got is 36 over 2, 36 cookies for 2 sheets. So what would the unit rate be then, Sean? 18 cookies. Oop, you can't. Thank you. 18 cookies per 1 sheet. So when it says the unit rate of y over x is 18 cookies, per 1 sheet. And then our constant of proportionality, again, is that 18 over 1. So the meaning of the constant of proportionality in this problem means 18 cookies per 1 sheet. So when we look at the constant of proportionality, one other thing to note here is that unlike rate, where we said we need labels on that, when we're talking about the constant of proportionality, we don't need the labels at that point, because now we're talking about a number which tomorrow we're going to be putting into an equation and working with. So the constant of proportionality usually doesn't have labels on it, where the unit rate and the rate does. So when it says it takes 2 hours to bake 8 sheets of cookies, if Brandon and his mother begin baking at 4 p.m., when will they finish baking? So how many cookies did they need to make altogether? No, not just 96.
288.
Where'd you get 288?
The 96 times 3.
Okay, so they have to make, I'm going to start over here, because they have to make, for each of those 96 students, they have to make 3 cookies. And so you say that was 288 cookies? 288 cookies. So using our constant of proportionality, if it is 18 cookies on one sheet, how many sheets is it going to take to get to 288 cookies? Go ahead and think about that with your group for a minute. Work on that. That we had to get between 18 and 288, we would have to multiply by 16. So if we multiply the denominator by 16, that would give me 16 sheets of cookies that they have to make to get all 288 done. But now we're going to look at another rate. In this problem here, we were given another rate. What rate were we given there? 2 hours to what? We have to have 8 sheets of cookies. So if we know that it takes 2 hours to do 8 sheets, how many hours is it going to take to do 16 sheets? Oops, sorry. Here 4. How are we getting 4? 8 times what is 16? 2. So 2 times 2 is 4. So if it's going to take them 4 hours and they start at 8, when are they going to? Or if they start at 4, when are they going to get done? They're not going to get done till 8 o'clock p.m. It doesn't say. Oh, 7th grade. Yeah, 7th grade. All right. We're going to be talking about the French cooking class. Wow, way fancier than baking cookies. Suzette and Margot want to prepare crepes for all the students in their French class. The recipe makes 20 crepes with a certain amount of flour, milk, and 2 eggs. The girls already know they have plenty of flour and milk to make 50 crepes, but they need to determine the number of eggs they will need for the recipe because they are not sure if they have enough. Consider the amount of eggs necessary to make crepes. What is the constant of proportionality? So with your group, talk about that. What is the rate of eggs necessary to make the crepes? Because it doesn't say necessarily that this has to, like the other ones that said we're setting it up for cookies proportional to the number of cookie sheets, but we don't have it telling us the way we have to set that up. Now, normally what we would look for, and I don't know if you guys have talked about this in science yet, is that our x, our number that would be on the bottom, because we talk about y over x, is the things that we can't necessarily control. So the number of eggs, we have to have 2 eggs, okay? How many crepes we get out of that is a little bit more of what we can control. And so we would probably set it up 20 over 2 to talk about that constant of proportionality. And so when it says, what does the constant of proportionality mean in the context of this problem, we would say you can make 20 crepes with 2 eggs. Again, I didn't label these because they're constant proportionality, although it's the same as rate. We're talking about a number that we're later going to put into that equation the y equals kx equation. So I don't necessarily need a label on it, which is why we're writing what that means. But then if it says how many eggs are needed to make 50 crepes, so if we have 20 crepes, got to make that fancy little thing on my E so I look fancy, and 2 eggs, we need to figure out how many eggs are we going to need to make 50 crepes. Okay, so with your group, go ahead and work on that. How many eggs would we need to make 50 crepes? Different ways here, and they were both fine. Some people did what we had talked about before, and they said, well, I want to know what times 20 would give me 50. So if I take 50 and I divide it by 20, that's 2.5. So 20 times 2.5 is 50. So that must mean I take my eggs times 2.5. 2 times 2.5, and I get 5 eggs. Other people I saw went through and they took that 20 crepes over 2 eggs and they found a unit rate. 10 crepes per 1 egg. And then they multiplied it by the 5 eggs that we'd need. And they got the same answer, which they should have. But it was just a different way to do it. And both ways of doing that are absolutely fine. But the idea is we're finding equivalent fractions, basically, that we're representing unit rate to find out what happens with an expanded number there. All right.